So the other day, one of the class, I was talking about the ln. How could you write ln k minus ln 2? That's ln k over 2 equals ln 4. So it's one of those log properties they want to make sure you remember. Well, if that's true, then k over 2 has to equal 4, so k would have to equal 8. Like that. Okay? So setting up your area, doing that, and then remembering that log properties. Okay, anything else? 39. Now this would be one you could use your calculator on if necessary. A lot of times it's not, but if you needed to. Okay, and they actually kind of looks like have written this so that you don't use your calculator, it looks like. And they often do that. In the calculator section, they'll put problems that specifically are worded in a way that the calculator really doesn't help much. So the graphs of cosine 2x and y equals sine x intersect 4 times. Let a, b, c, and d be the coordinates. Which of the definite intervals below represents the largest number? Now, like I said, I think when I assigned this, I said that there were 3 we probably couldn't do, and there are other ones in here that, yeah, maybe we can do, but they'll be a lot easier later on, right? I mean, we kind of have some of this knowledge, but we haven't really practiced or talked about a lot. So A, B, C, and D are all in between 0 and 5, and so if we have these functions, it says they cross 4 times in between there. Okay, so actually now that I look at this, now that I have read it, actually the calculator does help us here. This is one we would want to use our calculator on. Okay, and so let's just talk about this, and I don't want to spend much time getting the calculator out, doing it and all that stuff, but let's just imagine it kind of, one of them does this, and the other one comes through and, you know, does this. What does it mean to do the integral of one graph minus another? We've done one problem like this so far. Okay, so let's imagine this is point A, and let's imagine this is point B. The integral from A to B, and let's say the blue curve was the sine, okay, and the red curve was the cosine. So what area would that represent right there? It's the area in between. Remember that one problem we did where we had the 2 graphs, and we had one graph going up like this, another graph in here, and we were talking about the area in between. We said, well, if you did the area under this one, and then you did the area under this one, and subtracted them, you'd end up with the area in between, right? That's what we talked about. Horrible picture, but that's what we talked about, okay? So the area under one, the area under the other, you subtract it, and you get the area in between them. So one of the things we'll learn actually in chapter 7, that's when we'll do it, but if you had this picture, this area, and actually it doesn't even matter that it goes below the x-axis. One of the things we'll find out is when you have area between 2 curves, it doesn't even matter if it's above or below the x-axis, and think about why that is. If you take this blue and red, take both graphs and just shift them up or shift them down, does that area change in between the two? It's the same piece of area, right? Now, if you're doing the area between the curve and the x-axis and you move the curve, then that area changes because the x-axis doesn't move, right? The graph moves, so that area changes. So then it does matter. But when you're doing the area between 2 curves and you move both curves, that area doesn't change. So the x-axis actually doesn't matter. What matters, what determines if an area is positive or negative is which graph's on top. So if you do the top graph minus the bottom graph, that's going to be a positive area. Kind of like if you take 8 minus 5, you get positive 3. What happens if you do 5 minus 8? You get negative 3, right? So if you did an integral that had the bottom minus the top, then that would switch around, and that's how you would get negative area. Okay, so anyway, that's all stuff we'll talk about later on. So all this problem was about, says which one of these represents the largest number, would be looking at the graph and seeing which chunk of area between these curves was the biggest. But you would also have to pay attention to what order these were written too, Because if it's top minus bottom, that's positive. If they're bottom minus top, that's negative. Okay? So that's as much as I want to say about that one. I'm not sure what the right answer is. It's in the book here, but that's what you would do. Okay, so that would be one of those that, yeah, we haven't really talked about. I could have definitely put that on the list of ones that, like, yeah, you can't really do that one. But we talked a little bit about. I want to talk about 43 here, and then I want to move on to what we're doing today. Was this one I told you to skip or not? No. Okay. So let's talk about 43, and that was one of the reasons we really haven't done this yet. But we've talked a little bit we've talked about the units. Okay, and we've talked about how we had miles per hour, and when we do the integral, the area of miles per hour, what they give us? Miles. So isn't it reasonable that if I have a function that's gallons per hour, if I did the area, that might give me gallons, right? So what I wanted to talk about on this one, and you don't have to put it in your notes right now, but this is something we are going to really emphasize and really be talking a lot about, and this is probably the number one major use of an integral right here. And it's just an offshoot of what we've already done, which is that if you have a speed graph, then the area under can be the distance. Well, we can generalize that. If we have an integral of any rate of change, okay, then the integral is going to equal the net amount of change. Okay? And that is a huge big deal. I mean, it's just derivative in reverse. We talked about derivative. If you have an amount function, the derivative is the rate function. Well, now that we've learned about the integral and its relationship to antiderivative, it totally makes sense that this would be true. So if we have, and think about why that is. If I have the integral of f prime from a to b, fundamental theorem part 2 says that how will I find that? Right? Well, we just got done doing. Number 9 and 10 on the gateway test were definite integrals. What did we do with this? We do the antiderivative, which would be, what's the antiderivative of f prime? F, plug in a b, plug in a, isn't that net amount of change? I mean, think about that in terms of miles. So if this is miles per hour, this would be miles at the end, miles at the beginning. You take your ending spot minus your beginning spot, that's net distance traveled. That's displacement, right? So we can, instead of net amount of change, we call it displacement, but it's the same idea. But I'll go with net amount of change, okay? So it makes sense. I mean, that's what the fundamental theorem basically says, right? So if this is gallons per hour, then this would be the net change in gallons. So now, as we think about that, we look at this problem. So tank being filled with water at the rate of 300 t to the 1/2 gallons per hour. T greater than 0 measured in hours. The tank's originally empty, so that's good, because if it's net amount of change, so if we know it started at 0, then that's good. How many gallons are in the tank? Well, whatever its net amount of change is, since it started at 0, that's going to be whatever this integral is going to be how many gallons are in the tank. Now, what we'll find out is we'll have to be careful about how this is worded. If the question is how many gallons of water went in during the 4 hours, how much is in the tank. If it's how many gallons went in during the 4 hours, then that would be the net amount of change. If it's how much is in the tank after 4 hours, we got to take into account how much was there when we started. Now, since it's empty, those two answers are going to be the same in this problem. So this is all we have to do. So this is pretty simple if we understand that concept. Okay? And so this is when we get into the application ones in chapter 7. This is what problems will look like. All we have to do is get the integral set up, and most of the time we'll just use our calculator and solve it, which this is a calculator problem. So right now you can just type that into your calculator and go. The hard part of the problem is setting up the integral. And to be honest, it's not usually that hard. Okay? It's not near as hard as setting up those story problems were back in the derivative scenario. Okay, so you can just type this into your calculator, and I don't know which one you get, but whatever. That's all you do. Okay, but that's a really key concept that we will be using a lot going forward, is that right there. Okay? And again, it comes back to what we've been doing here. Okay? All right, so let's go ahead and put those aside for right now and take a look at or get your notes out. And also you need the hats. So those got passed around. There's some back there, looks like. There's a few here. Okay, I'm going to send you a. And I probably should start the class. You should go ahead and try to log in now. You should be able to log in. So this is something that I put up here at various times already. So a definite integral. So we've spent a lot of time talking about indefinite integrals, right? Which is this idea of finding the antiderivative. And that's all because of number 2 here, right? That's all because of number 2. Number 2 is a big deal. It's a great way for us to find these integrals. But now, if you think about what we just got done talking about in that problem about gallons per hour, we've now arrived at an entirely new reason for having an integral, right? It's not just about area. It's not just about area. So when we looked at the definite integral from A to B, that's all it was about in the beginning, was area underneath a graph, okay? But now we just showed a definite integral that said if you have a function in there that's a rate of change, doing the integral of it gives you the net amount of change over that time period. And that doesn't have anything to do with area, right? Now, we could take that rate of change function, we could graph it, we could do the area under it, and that would give, that number would be the number that's net amount of change. So it's got, just from that alone, it's got a lot of uses that we could, places we could use it. Now, but now let's think back to it as an area. Now remember, a definite integral is just a number. That is just a number answer. Okay, a definite integral is just a number. How can we get that number? Well, we can think of it as an area under a curve, and we can have some geometric shape. Or we learned about the fundamental theorem, the whole process of antiderivatives. Now we've practiced it and gotten good at it, hopefully. And then all we have to do is plug in the b, plug in the a, subtract them. That's a great way to get that number. However, and let's go to our calculators. Okay, not everybody's logged in yet, but who wants to be the presenter? Take off the names. Who's that? Matt. All right, go onto the calculator screen, if you would, and do the integral, indefinite integral. And I think I've shown you this before, but let's do the indefinite integral of sine x dx. Okay, and now do the indefinite integral of sine of x squared. Put an x squared on the inside. And what does that tell you? The calculator can't do it. Well, it turns out there is no antiderivative. There is no antiderivative of sine of x squared. There just isn't. Okay? Now, let's do a definite integral. Take the top one, and let's do the definite integral from 2 to 5. No, the top, this just regular sine x. Just regular sine x. Okay, and see the answer it gives us, because what the calculator is going to do, we're in auto mode, which auto mode means it's going to try to give you an exact answer if it can, right? So what it does is it gets the antiderivative, does f of b minus f of a, and writes out that answer. Now, a lot of times that's not that useful of an answer. We'd rather have a decimal because it might be a story problem, it might be a number we're interested in. So we might hit control enter, but that's fine. So now do sine of x squared. Now go ahead and just grab that. Yeah, now change it to an x squared in there. Okay, now, yeah, go. All right, anyway, what I was going to say was, how's the calculator going to do it? I mean, we already saw that it can't do an antiderivative. There is no antiderivative. So how's it going to do it? But if you graph this, right, if you graph sine of x squared, it's going to make a graph. And there's going to be an area from 2 to 5, right? I mean, there's going to be an area. So what did the calculator do? Right? How did the calculator come up with that area? And it's an approximation. That's what it does. And so it tried, it looked at it and said, is there an antiderivative? Can I do f of b minus f of a? And the answer is no. So it still gives you an answer. So then the question is, how exact is that answer? And I think the calculator is programmed to, I don't have exact information on this, but those are all, that is the exact area up to that many decimals. Okay? So chapter 6 is all about how does it know. If there is no antiderivative of this, which means we can't know the exact area, then how does the calculator know that that's the exact area up to 12 decimal places? And that's what chapter 6 is going to do. But for right now, we'll just trust, okay, that that is the exact area up through that many decimal places. Okay? So, back to this. So, this didn't work because the graph, if we looked at it, would not make a geometric shape. It doesn't have an antiderivative, so we can't do that. But we figured out that if this is a rate of change, we might be interested in the net amount of change. We might be interested in that connection, being able to do it. So we have another way, and that's approximation. So that's the part we're going to get into today. Okay? All right. So I'm going to send you, before we get into this, I'm going to send you a couple of documents here. One is called Riemann sums, and one is called LRAM, RRAM, MRAM. Okay, and I would say let's open up the one that says the last one I gave you, the LRAM, RRAM, MRAM. Let's open up that one first. A little early. Hey. I can wait if you teach. You have good timing. Yeah, you just got it. All right. So, everybody got this one open? All right. So now, again, these documents are more for you to just play around with. We're just going to play around with it a little bit right now. Not a big deal, but sometimes the visual and being able to manipulate it yourself a little bit is good. If you go forward a few screens, control right arrow is how you can see these different things. Okay, so what we have here on this page, the 1.6, if you get to 1.6, now remember when we first started this, and I put up that slide with the speeds, you know, at 0 it was going 20 feet per second, and then at 1 it was 30 feet per second, and 38, remember that? And I said how far they went in those 5 seconds. And then I drew pictures of that. Well, think of this as the same thing. Okay, if I want to do the area underneath this, okay, one way to do would be to look at just these intervals, just like we did on that problem at 1 second, at 2 seconds, at 3 seconds. And if you remember how we talked about it, we said, well, maybe the first second, they just kept going 20 feet per second the whole first second. and then the next second they went 30, and then the next second they went 38, and the next second they went 44. Remember that? We said you could add those up, and that could give you a number, but that would probably be an underestimate. Probably they were accelerating that whole time. So we're interested in this area. Well, those 4 rectangles, and this goes back to the first or second day of class, we did some of this too. Okay, remember you guys, some of you froze up your calculators trying to do 10,000 rectangles or whatever, right? It did. Yeah, so that's what we're back to now. So the idea is, okay, if we did 4 rectangles here, and now these are, why is this called LRAM? Well, this LRAM stands for Left Rectangle Approximation Method. Left Rectangle Approximation Method. These are called, what you're looking at right here, are called left rectangles. Okay, because these rectangles touch the curve at the left edge of the interval. Or actually what we'll call a subinterval, because our interval is really the interval from 1 to 3, right? We're really doing the integral over the interval 1 to 3. And so we've divided that interval into 4 subintervals, okay? So each of these would be what? 1/2. So this would be 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3. So each one is 1/2 wide. And at the left edge of each of those subintervals, we've plugged into the function, got a y value, and drawn a rectangle. Okay? So what do you suppose RRAM stands for? Right rectangles. So these are 4 right rectangles. Okay? Divide up into 4 subintervals. Each rectangle hits the curve, and the function value, the y value, is the height, and the subinterval width is the width of the rectangle. And where the height is being determined at the right edge of each subinterval. So this is clearly an over approximation of the area, right? And then MRAM, these are called midpoint rectangles. Midpoint rectangles. So we go to each subinterval and we go to the midpoint of that subinterval, go up to the function, and that's our height. And now that looks a little better because that way we get a little above, a little below. So midpoints look like they would be better than left and right, okay, as far as an approximation. All right, and so then they give you the area of each one, and I think that's the last page. Okay, so that's just a good, and there's pictures in your book too, but that just gives you a good picture of a left rectangle, what a right rectangle is, what a midpoint rectangle is. Okay, let's go to the other document. If you could open that up. Go to, you can go back to your home screen. You can go to My Documents. Okay, go back to the home screen, go to My Documents under the AP Calc Block 1. And it's called Riemann sums. Riemann sums. Now that's Riemann is actually a guy's name, George Bernard Riemann, German name, I think. Okay. What's that? Well, for a set number of rectangles, right? If you're going to do 10 rectangles, 10 midpoint rectangles will always be more accurate than 10 rights or 10 lefts. Okay, so now we're going to define what a Riemann sum is here in a minute. But what this one allows you to do is play around with all of the different ones. And so you can drag, so these are left rectangles, you can drag this point over here and you can get midpoint rectangles, you can drag this point over here and get right, you can drag this point over, now it's not real handy, and you can get trapezoids. If you remember, we did talk about trapezoids too. Now trapezoids look really accurate. Now, this is not a big deal for us right now, but along with Harisha's question, it actually turns out that 4 midpoint rectangles are actually going to be more accurate than 4 trapezoids would be. Now they're really close, and we'll talk later about the connection between them. But visually, trapezoids always look really good because you're kind of estimating that. They just look like there's a good fit. There's just a small amount of area here that's going to be off. But midpoints for any given number of them, midpoints actually approximate a better. Now, as we're going to find out over the next today and Monday, it doesn't really matter, because what we'll do is we'll just do a bunch of them, right? And so if you do enough of them, left rectangles can be as accurate as you want to be. Right rectangles can be as accurate as you want to be if you do enough of them. It just takes more of those to be accurate. Okay, so if we were doing them by hand, that would be important to us. You know, we are going to do some by hand, but we're not going to do a lot by hand, right? And we'll kind of have a rule for that, which we'll talk about. All right, so anyway, that's how we can approximate. We can calculate these rectangles, calculate these trapezoids, and we can get an approximation for the area. And that's kind of what's going on behind the scenes with your calculator, okay? And that's something we're going to learn about as we go along. Okay, so let's go back to your notes here, and let me see if I'm ready for this. I think I am. Yeah, let's go. This is number 17 in the book. You're going to have some like this in your homework, okay? And so, and then there is some work to this, guys. I mean, there's some writing out of stuff. Now, you gotta trust me a little bit here, in that I'm not having you write these out. I'm going to be pretty picky about how we write these out. And it may seem like it sometimes, and it feels like busy work writing it all out. But what you'll find out is, at the end of it, what we're looking for is we're looking for patterns. And the patterns are easier to see if you write stuff out. And that's the key. And that's why we're writing it out. Okay, so number 17 in the book. This is on page, this is 5.6 is where we're at. So number 17 in the book is on page 355. So it says, so I'll let you go ahead and draw this sketch. This is x cubed. We want to do the integral from -2 to 2. Okay. It says, draw a sketch that illustrates the approximations L4, R4, M4, and T4. Then compute each approximation and compare it with the exact value of the integral computed using the FTC. Okay? So I am going to draw we're going to draw 4 of these, okay? And what do you suppose an L4 means? 4 left rectangles. That's exactly what that means, okay? So we're going to, and we want to draw a sketch that shows L4, R4, M4, T4, then compute them, and then compare with the exact value. Okay, so let's just do the exact value right now up here. We all know that the antiderivative of that is going to be 1/4 x to the 4th. We're going to go from -2 to 2. So we plug in our 2. That's going to be 16 times 1/4. So that's going to be 4. We're going to plug a -2 in. That's going to be 16 times a 4th is going to be 4. 4 minus 4 is 0. Oh, shocking that area is 0, right? Of course that area is 0. Right? It's an odd function. It's got symmetry. We got negative area. We got positive area. We cancel each other out. Of course, we should get 0 as our area. Okay, now we're going to do, so that's our exact area computed using the FTC. So now in L4. So here's what we're going to do. We're going to practice. Notice I put some points in here. 1, 1, 1, -1, or -1, -1, -2, -8, 2, 8. I've got those points up here. Okay, now, another little formula that's going to be important for us is B minus A divided by N. Okay, so B minus A is our total width of our interval divided by how many subintervals we want. So N is going to be our subinterval. So when we talk about L sub N, right, the N here is 4. We want 4 subintervals. So this is going to be 2 minus -2 divided by 4, which of course is 4 divided by 4, which is 1. So each of our subintervals is going to be 1. So I'm going to go ahead and mark those. Right? Now notice there's 5 points there that make up the 4 subintervals because you got your beginning and your end. Kind of like when you learned about sine graphs last year. You went from 0 to 2 pi, you divided it up into 4 parts, but you had 5 marks that did that. Well, the same thing is true here. 5 marks will make up 4 subintervals. Always one more. Okay, so how do we do a left rectangle? Well, we start on our left edge. We go down, in this case down to the function. We go over 1, and we draw back up. That is one left rectangle. Now, you would think drawing rectangles is pretty darn easy, but you'd be amazed how many times we screwed this up. Okay? All right. Then we go to the next subinterval. And we go down to the curve, which takes us down to -1. We go across 1, and then we go back up, and there is our next left rectangle. Okay? Then we go to our next subinterval. We go to the curve at the left endpoint. Where does that take us? Right there. We go across 1. There's our rectangle. I usually draw it kind of thick there, just so you know we're doing something there. But that left rectangle actually doesn't exist. There is a left rectangle with a height of 0 right there. But that's our third left rectangle. And then the last left rectangle, we go to this point, and we go across 1, and we got that. Okay? Now, so they told us 3 things. They said they want us to do the integral with the fundamental theorem. We did that up there in red. They want us to write out, or they want us to sketch L4, which we just did. And then they want us to compute the approximation. So here's how I want you to write this. Okay? I want you to write the height of this rectangle, which is f of -2. I want you to write it like that in f notation. I want you to write f of -2 times, and then what's the width of that rectangle? 1. Now I know it's silly to write a 1 times a 1, but we're going to do it. Because when you look at this, again, thinking about patterns, when you look at this, I want you to see a rectangle height times a rectangle width. And the f is the y value, that represents the height. Okay, what's the next one? It's f of -1 times 1 plus f of 0 times 1 plus f of 1 times 1. Okay? Like that. Now we go ahead and we calculate it. Well, it's a pretty simple function. If we get a more complicated function, this is why I didn't want to write -2 cubed here, because if it would have been a more complicated function, that would have been a lot to write out. It's better to write it in F notation. Now you can say, okay, now let's plug a -2 in. So we get -8 plus, now we put in a -1, we get -1, plus we put in a 0, we get 0, plus we plug in a 1, we get 1. Now that's clearly going to be the areas of all these 4 rectangles. We got -8 area, -1, 0, and 1. Okay, and so that adds up to -8, which is clearly an awful approximation of our exact area, but 4 rectangles is probably not going to be a very good approximation generally. Okay, and you can see we have way more negative area than we need, and we didn't account for our negative in that. All right, okay, draw it again, and we're going to pick up the pace here. Again, doesn't have to be real fancy, but, you know, your next quiz we take, I don't know if it'll be next week because we got that goofy day with the careers. Whoops, I shouldn't have said goofy. We got that exciting, and I think it will for seniors, junior seniors. I think the job shadowing, I think that stuff's actually pretty cool. Getting a chance to do that. But anyway, I don't know that we'll get to the quiz next week. It'll probably be the beginning part of the next week after that. But on the next quiz, you will definitely be drawing some rectangles, right? You'll definitely be drawing some rectangles and computing and doing this. Okay, so now L4, that was L4, so let's do R4. Okay, let's do R4. Now, same marks, right? This time we're going to go to the right edge and draw backwards. Right? We're going to go to the right edge of the interval, and draw backwards 1 unit. Okay? Next subinterval, we'll go to the right edge and draw backwards. Go to the right edge and draw backwards. Go to the right edge and draw backwards 1 unit. Okay, so you're going to have a problem similar to this tomorrow as part of your homework, and for Monday, not tomorrow, for Monday. And then there's another problem. Well, you're going to have like 5 problems where each one of the problems is a drawing, right? So you have one problem like this where you have 4 drawings, and then you have a number of these drawings of rectangles. Okay. So R4, so what's this? So now this starts, instead of f of -2, what's our first right edge? Is at -1. So this time it's going to be f of -1 times 1 plus f of 0 times 1 plus f of 1 times 1, which is where we stopped last time. This time we go all the way to f of 2 times 1. So that's going to be -1 plus 0 plus 1 plus 8, which is going to give us a total area of 8, okay, which, again, is obviously way too much positive area, we can tell from our picture. All right, so now let's talk about midpoint. So the midpoint ones and the trapezoid ones are a little more interesting. So go ahead and draw a quick sketch for, again, mine's a little better, but if I'm you, I'm going like this, 1, 2, yep, oops. Right, doesn't have to be beautiful right now, okay? But anyway, so now we're doing an M4, okay? Well, again, we still have our 5 important marks. Even though I know we're going to do midpoints, we still have our B minus A over N. That's still, the width isn't changing, right? This is still 2 minus -2 divided by 4. This is still a width of 1. The rectangles are still a width of 1. The only difference is we go into the middle here, and so a lot of times I'll make these marks real big, and then make these midpoint marks smaller. But we go into the midpoint, and we go in here, and we get this number, right? And then we draw half that way, and there's our rectangle. Okay, so we go the middle of the subinterval to the curve, and then we draw to the left and to the right. So I go into the middle here, which is going to be right there, and I'm going to go to the left and to the right and make this little rectangle. On this one, I'm going to go halfway in the subinterval up to the curve, left and right. Go halfway in this subinterval, go up to the curve, go left, and go right. So this one is clearly better already. Now, how do we want to write this? Our first height. So I want to try to use the same language all the time when we do this. So the first height is measured where? -1.5. Now, we want to use decimals. That's fine. Some of this may be done without a calculator, so I probably would go -3/2. Here's another reason I'm going to do it that way, is because when we get to patterns later on, a lot of times fractions, it's easier to see the patterns than it is with decimals. Okay, so our width is still 1. That rectangle is still 1 wide. Okay, what's the next one? -1/2 times 1 plus f of +1/2 times 1 plus f of 3/2 times 1. Now I'm going to let you use your calculators at this point. So to be honest, right, I'm going to let you type these into your calculator. So getting the cubes you know, might make more sense in decimals. Then when we get weird fractions, that's not as nice. But I could cube this. I mean, it'd be negative 27/8. You know, this would be negative 1/8 plus 1/8 plus 27/8, which actually equals what? This one actually is going to hit it exactly right on, isn't it? But that's kind of coincidence. It's not usually that good, a midpoint, but it just turns out because of symmetry, this one's actually going to do that. But it would be okay for you to put them in decimals if you wanted to at this point, you know, whatever. All right. All right, let's talk about trapezoid real quick, and then we're gonna do a definition here, and then I'm gonna help you. We're gonna work the first one in your homework together. Okay? Because this is basically what the emphasis on the homework is: drawing them, calculating them. Right? That's what we want to do. All right, let's finally just do the last one, which would be trapezoids. Okay? Trapezoids. And you can see why you don't want to draw these all in one graph. I mean, this would be a nightmare. The way this would look. But if we're going to do 4 trapezoids, now trapezoid formula is kind of ugly, which is why we do most of our work with rectangles. Okay, notationally, the theory part that we're going to be getting into, we're going to work with rectangles because the trapezoid formula is just messy. Now, if I'm really interested in an approximation, a trapezoid is not a bad one to do. Okay, and we'll be talking about a lot of that. All right, now, remember, a trapezoid is 1/2 the 2 bases times the height. Now remember, these are going to be trapezoids tipped up on their end. So what's our h going to be in these problems? Our h is going to be the 1. Okay? So again, I'm going to mark my 5 marks here. Right? Like so. And so how do we draw a trapezoid? Okay? Well, we have to draw a height at the left edge and at the right edge, and we connect them. In other words, it's going to look like this, this, and connect. That's what we mean by a trapezoid. Okay? So we're going to go to the left edge and go to the curve. We're going to go to the right edge and go to the curve, and we're going to connect those as best we can with a straight line. Okay? Now, sometimes a trapezoid, well, you're going to see in this next one, is not really a trapezoid, it's a triangle. Okay? Because look what's going to happen on this next one. We go to the left edge, which is here, the right edge, which is a 0, and we connect them. It's actually a triangle. That's okay. That's okay. It just means one of our B1 or our B2 is going to be 0. And if one of those is 0, what do you got? You got 1/2 base times height, which is a triangle. Okay? All right. And then the next one, you go here and you connect. You go up here to here and you connect. And there's a trapezoid. Okay? That's what your pictures look like. All right. Now what's the calculation look like? Well, trapezoid is going to be a little messier. So we're going to have a 1/2. What was my B1 then? Let's use F notation. F of -2 plus F of -1. This is the left edge, this is the right edge of that trapezoid. And then times our 1. Again, I want to see in your work, because we're going to need this later when we need to see patterns. So we need to be good at this and just boom, writing it down, writing it down, writing it down. I want you to see a trapezoid. When you look at this, I want you to see a rectangle. I want you to see height times width, height times width, height times width, height times width. When you look at this, I want you to see a trapezoid there. That's one trapezoid. Plus, next trapezoid would be F of -1 plus F of 0. Notice how we used -1 twice. It was the right edge of the first trapezoid. It's the left edge of the second trapezoid. And then times 1. Okay, next trapezoid, 1/2. It's going to be F of 0 plus F of 1 times 1 plus 1/2 F of 1 plus F of 2 times 1. Okay? Notice you use them all twice except first and last, the ones at the end. Okay, that's a pattern that's going to come in handy later on. Okay, well, we already know that's -8 and that's -1. We know that that's -1 and that's 0. We know that's 0 and that's 1. We know that's 1 and that's 8. So we're going to get -9/2, plus here we're going to get -1/2, plus here we're going to get 1/2, and plus here we're going to get 9/2, which of course is going to add up to 0 again. And again, that's a coincidence because of symmetry. That's not going to happen most of the time. Okay, but just because of the way we picked this one, it works out. So trapezoid midpoint both hit the exact area, but that was just coincidence. All right, so drawing and writing out something we want to be able to do. Okay, so this is an important definition. Okay, Riemann sum. Now, Riemann, again, this is a guy's name, German fella. I want you to think, when you hear Riemann, think R for Riemann, R for rectangle. R for Riemann, R for rectangle. A trapezoid is not a Riemann sum. It's an approximation technique, but it is not a Riemann sum. Riemann sums are rectangle sums. Okay? All right, so a Riemann sum is this. Let the interval AB be partitioned into n subintervals by n+1 points. Right? We just talked about that. We just did one where we divided it into 4 subintervals using 5 points. Right? So that's where that n+1 comes in. Okay? A is the left edge, which we're going to call x sub 0. Since we have n+1 points, we got to start counting at 0. And we want to end at n, and that'll give us n+1. Okay? So A, our left edge is going to be A, which is going to be x sub 0, which will be less than x sub 1, which will be less than x sub 2, which will be less than x sub 3, all the way out to x sub n+1. Oh, whoops, that's not right. Jeez. How many years have I written that? What should this be right here? No. n-1. Right, like x sub 7 and this would be x sub 8, right? That n-1 is the one before it, right? Okay, and the last one is n. Now that's n+1 points because we start counting at 0, right? So if you have 10, right, if you have 10 subdivisions, you go 0 through 10, that's 11 points, right? 10 subdivisions would be 11 points, okay. So all this is saying that x sub 0 is to the left of x1, which is to the left of x2. We just go down, that's all that's saying, okay, so easy. All right, so we're going to partition it, which we just saw. Let delta x sub I, delta stands for change in x, so it's slope. We did rise over run, delta y over delta x, change in y over change in x. So delta x is our change in x. That's our subinterval width. That's our width. Now, why do we have delta x sub I? Here's why. Because we don't have to do equal width intervals. 99% of the time we will. We'll divide it up into equal subintervals. But we don't need to. And we'll talk about tomorrow. There's a picture in your book. Well, you can probably flip back to it since you probably read your book anyway. If you go back to page 351, if you happen to have your book out, you go back to page 351 down the bottom of the page, they show some rectangles where some are skinny, some are fat, right? They don't have to be equal widths to be a Riemann sum. It just makes sense to do it most of the time. So we do that, okay? But they don't have to be. So delta x1 could be your first subinterval, delta x2 could be your next subinterval, delta x3 be your next subinterval, right? So delta x sub I is the width of the ith subinterval. Okay, so we're just getting some stuff down here. Within each subinterval, let C sub I be your sampling point. Now, what sampling points have we used so far today? We've used the left edge, we've used the right edge, and we've used the middle. But will we have to use one of those three? No. We can make rectangles where we go a third of the way in to the subinterval, and then go up to the curve, and let that be our height. And the next one, we can go a fourth of the way in, and let that be our, you see what I mean? So this, a Riemann sum could be any set of rectangles. We just choose to stick with left, right, and midpoints most of the time. Okay, so C sub I is going to be our sampling point within the subinterval. Then this sum right here, f of C1 times delta x1 plus f of C2 times delta x2 plus dot, 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 all the way out to f of Cn times delta xn. So now you can see a little bit why I was making you write that out. So this sum, and what would f of C1 be? What would f of C1 represent? Well, the C is the sampling point, but f of C1 would be what? The output, the y value, the what of the rectangle? The height of the rectangle, yes. Remember I said, I want you to, when you see this, I want you to see height times width, height times width, height times width, height times width, right? Which is area, right? So when you see this, I want you to see areas, right? Height times width. So f of C1 would be the first height, delta x1 would be the first width. Multiply those, you get the first area. F of C2 is the second height, delta x2 is the second width. Multiply those, you get the second area. You add those up, you have a Riemann sum. So this sum is called a Riemann sum for f on the interval AB. Okay, so I mean, there's a lot of gobbledygook there, and a lot of fancy talk for this, but you'll see tomorrow where we're using how we're using this. But okay, so that's why I say Riemann sum. Think rectangle areas. Riemann sum means rectangle. Sum, of course, means add. We're adding up rectangle areas. That's what a Riemann sum is. Okay? All right. Which is how we can approximate an interval. All right. So, number one in your homework. Now, let me see, make sure I'm not skipping something. Nope. Okay. So, you're going to do 1 through 6 on page 354, and 1 through 6 all use this picture. Okay? Now, if you want to lay your book over, or your paper over top of the book and trace it, or you just want to draw a quick sketch of it here, but you're going to have 6 pictures. Right, when I come around and look, that's what I'm looking for is 1 through 6. You'll have a picture, one picture per problem. Right, so we're going to do 1 together, then 2 through 6 on your own, and then problem 16. There's a couple other problems I have, but you don't have to draw. You don't have to draw anything for those. Okay, and then on number 16, which is just like number 17, you'll have 4 pictures drawn for that. Okay, so you have 10 pictures total that are drawn. On 7 and 10, you just have to calculate. Okay? You just have to write out the calculation. Okay, so I'll give you a second if you want to draw it. Okay, I just went through and I picked out some of the important points, some of the points that crossed right at nice points on that grid. I don't know. Let me see my grid. No, not really. Oh yeah, I guess it can. So we're going to do it backwards. So on number 1, it says estimate by evaluating with 5 subintervals, and then draw a sketch. I'm going to draw the sketch first, and then I'm going to write it out. Okay? So this is G, this is a graph of G, and so we're doing the integral from -5 to 5 of G of X dx. And we're doing an L5. Okay? A left sum with 5 subintervals. Okay? This is -5 over here. This is 5. Some of them, they don't have you go the whole way. I think number 5 only goes part of the way. 6 only goes part of the way, so you don't do the whole thing. Okay, so the first thing we should calculate should be what? If I'm ready to draw them, is what? The what? Well, no, we didn't have to do that because they don't give us an equation. Yeah, so we have no idea what the actuary would be. Okay? The interval, the subintervals, the width, the b minus a over n. So 5 minus -5 divided by 5, which is 10 over 5, which is 2. So this is a total width of 10. Total width of 10. I'm going to do 5 subintervals, so my width is going to be 2. So I want to do left rectangles, right? So I'm going to go to my left edge. So I'm going to go ahead and put in, I'm going to need 6 points, right? If I'm going to do 5 subintervals, I better have 6 points. There would be my 6 points right there. Every 2 units. So width of 2, width of 2. Now I'm not saying you have to go in and draw those 6 points. I mean, you've got your marks there already. That's fine. But I would just find it helpful, just like with sine curves and cosine. Okay, so left, I'm going to go to the first, I'm going to go to the left edge and go to the curve. And I'm going to go over how far? I'm going to go over 2. There's my rectangle. Now I'm clearly missing the area by a bunch, right? I'm getting a bunch of negative area there that's not really on this. But we don't worry about that right now. Right? We're not worried about it. Okay, now I go to my next subinterval. Left edge, go up to the curve, go across 2. And then down. Alright? Next subinterval, left edge, up to the curve, over 2. Where's that fourth one going to be? Right there. Right? Because there's nowhere to go. This subinterval, the left edge, the y value is right at 0. So there's nowhere to go. So it's right there. It's an area of 0. And then the last one, left edge, go to the curve, over 2. 1, 2, 3, 4, 5 left rectangles right there. So we just did part B. Okay? Part A is to evaluate it. I want you to write it out. So we're going to write G of -5 times 2 plus G of -3 times 2 plus G of -1 times 2 plus G of 1 times 2 plus G of 3 times 2. And notice we don't make it to the far right edge, do we? Our last left rectangle is evaluated at negative, or not negative, at +3. Right? We don't use the 5 at all. But there's 1, 2, 3, 4, 5 rectangles right there. You can count. Okay, now all that's left is to get those values. So -5 is down here at -2. G of -3 is up here at +2. G of -1 is up here at +3. G of 1 is right here at 0. And G of 3 is down here at -1. So we've got -4 plus 4 plus 6 plus 0 minus 2. Looks like a total of 4, if I did that right. Does that make sense? That's what I want to see on 1 through 6. Okay, so that's number 1 right there. So you've got your sum evaluated, you got that, you got your picture. Okay, so the homework is 1 through 6. On 7 and 10, oops, not 7 through 10, 7 and 10, all you're doing is this part here, evaluating the sum, just writing it out. They give you the graph there. You can just kind of visualize what the rectangles will look like. We're just going to write out the sum. And that's where we're headed with this. We'll spend a lot of time writing out the sums, not always drawing, okay? But we need to be able to draw them. Because the more of them you draw early on, the better you can picture it as you're writing out your sums, okay? So we need that. Trust me, it'll come in handy. And then 16 is just like number 17 that we did, and that's it. That's your assignment for Monday. Okay? So 16 is the one you're going to have 4 drawings, an L4, R4, M4, T4. Okay? All right.
1 through 6, do we just do?
1 through 6, you do just what it says to do. Okay? So if you read number 2 says to do a right with 5. Yeah, so it tells you in 1 through 6 what to do. Right? It tells you how many subintervals to do, left, right, midpoint, trapezoid, whatever. Yeah.
So when you were showing us this program earlier, are those just programs off the computer?
What do you mean programs? That program?
Yeah, like that.
The one that did the number of things. Yeah, that was actually one, I think that one was one that I wrote. That one that did the rectangles. Yeah, now I got the idea for it from somebody else, because I used to do it on older graphing calculators we had, and so then I just adapted it for this. But yes, you can, like on Texas Instruments website and stuff, you can find different things that you can download and then connect with the connecting cable, that comes with your calculator, that USB one. And then that's how you get them on there. You can write them actually right on your machine. It's not nearly as nice. So there's software that you can get from Texas Instruments where you can type it out and then transfer it. So.